Okay, so we've had some success at writing acid-base reactions and titrations, and we can do various kinds of number crunch to determine how much acid it will take to neutralize this base or vice versa. Another way that we can follow the progress of a reaction like this is to track the pH as we add an acid to a base or a base to an acid and see how the pH changes as the acid and base fight in the solution. So what we've got here is a reaction where we take some strong acid, they're not saying which, and they're adding sodium hydroxide to it. So we have, we'll just call it HA, some kind of acid, and we're adding hydroxide to that. You know what? This is actually, because it's a top 6 acid, we can just say H3O. All strong acids turn into this when they hit water, so we don't really care what the original acid was. And as this happens, they want us to graph the progress of the pH. Before we've added any base, the pH is sitting at 1, which is a good strong acid kind of number. After we've added 5 milliliters of the base, the pH has crept up a little bit to 1.2 because we've destroyed a little bit of our acid. So 0, 10, 5 is halfway in between. 1.2 would be like there. 10 milliliters gets us 1.4, just below half. 15 gets us to 1.6, just above half. 20, we're at 2. 22 and a half. If this is 20 and this is 25, then 22 and a half is right in the middle. That's 2.3, so something like that. 25 mil, we're at 7. 27 and a half mil, we're up to 11.7. So if this is 25 and this is 30, 27 and a half is right in the middle. And 11.7 is something like this, just a little above half. 30 mil, we're up to 11.9, just a smidge below 12. 35, we're up to 12.2. 40, we're up to 12.4. And 50, we're up to 12.6. Now, not exactly a straight line. If we connect those, it turns out this is a very typical look for what we call a titration curve. They generally have a flat section at the beginning where it seems like nothing much is happening. This is the section where the solution is overwhelmingly acidic. When you drop in some OH, it gets quickly destroyed, and the amount of acid is going from like 1,000,000 to 900,000. That's still overwhelmingly acidic, and that translates into a very low pH. But the amount of acid is running out, and when you get down to here, the solution is still more acidic than anything else, but there's not enough acid left to resist very much more base. And if you keep adding base, right about here would be the point where there's virtually no acid left. There might only be a few million or billion acid molecules in the entire solution, and that means if you add just a little bit more base, those last few acids are destroyed and the solution goes neutral. And if you add just another drop of base, the solution swings to where now you'd have to call it basic. There's now base and basically no more acid, and so that causes a rapid spike in the pH. And after that, the solution kind of saturates with base to the point where adding more base, like if you have 500,000 people in a country and then you add another 1,000, yes, it's an increase, but proportionally it doesn't make that much difference. So this represents the acids slowly running out. When the acid runs out, we quickly blow through neutral and the solution swings from acidic to basic and then flattens out again. That kind of S shape is what we're used to seeing for a titration curve. Now, right in the middle of this, right in the middle of the spike, we identify a point, and we call this the equivalence point. You remember when we were doing our titrations, we always said that the number of moles of acid was equal to the number of moles of base. Sometimes it was 2 times the number of moles of base, or it would be a 2-to-1 or a 1-to-2 ratio, but in general, assuming it's a 1-to-1 reaction, we'd say the number of moles of these two things were the same. That's only true right here at the equivalence point, and this is the point where we consider our reaction to be done. The base has successfully neutralized all the acid because for every acid molecule that you used to have, you've added 1 mole of base to kill it. Down here, that hasn't happened yet. We have a lot of acid and we've only added a little base. Now they're getting close. Here they are exactly the same. And over here, the amount of base that we've added is actually too much. We've overdone it and pushed our solution over to the basic side. So this point, if we're doing a titration, this is where we want to stop, because this is where the number of moles are equal and all of our math is going to work. So we try to land exactly on that point. That point is the equivalence point, and you find it by looking for the big vertical spike in the middle of your curve and hitting the exact center of that. It won't always be at pH 7, but in this example it is. If you have a strong acid versus a strong base, then the equivalence point will be at pH 7, and that's another thing that makes it easy to find. Now, they ask us a couple more little things about this. They say, find the concentration of the acid, and what indicator would we use for this? Well, we started our reaction, and I didn't finish it, but I will now. The reaction was strong acid versus hydroxide, and that'll produce H2O plus more H2O. The point is it's a 1-to-1 ratio. And what information did they give us? 25 mil of a strong acid. 0.25 liters. 0.2 mole per liter sodium hydroxide. And one of those is a volume and one is a concentration, so we'll keep those in separate rows because organization makes me happy. Now, we need one more piece of information, and what we have down here is the milliliters of base that were added. And looking at our table, if this is our equivalence point, this happened when we had added 25 milliliters of base. So our volume for the OH, 0.025 liters. Now that we have that, we can find a number of moles for the hydroxide. Its concentration times volume, it'll be 0.005 moles. Because these are 1-to-1 and we know that our numbers of moles are equal, we must have 0.005 moles of acid also. And so our concentration for this would be number of moles divided by volume equals, and funny thing, it comes out to 0.2 moles per liter again. So that's our concentration for the acid. That's not surprising because look at these equal volumes of acid and base. That only makes sense if they're equally strong. If 25 mils of acid will neutralize 25 mils of base, that implies that the two of them have the same concentration, and indeed they did. So that's our concentration for the acid. The other question is, what indicator could we use for this? Now, you have a table in your data book. What page is that on? It's near the back. It is in the 2010 data book. It's page 11. Sorry, 10. Page 10 is the acid-base indicators. What these are, they're chemicals like food coloring that change color depending on what pH they're in. And for each of them you have a range of pHs, and next to that a range of colors. And the idea is if your pH is up to this first number, you get the first color. If your pH is after the second number, you get the second color. And if your pH is between these two numbers, you get a color between these two. So methyl violet would be Yellow, for anything up to pH 0, any negative pH also it would be 0. If the pH is between 0 and 1.6, you get the color between yellow and blue, which is probably green. And after you hit 1.6, methyl violet is blue, and it continues to be blue for the rest of, for any pH higher than that. So this indicator is good for catching when things are between pH 0 and 1.6, because that's when it turns green. When you see green color, you know, okay, that thing you were waiting for, it just happened. In our case, though, we're interested in catching this equivalence point, which happened right at pH 7. So we're shopping for an indicator that will change color right around 7, preferably one that kind of straddles 7. So 0 to 1.6, no, not even close. 0 to 1, no. 7, nah, this is a maybe. We might consider using Cresol Red. Cresol Red would be yellow up to pH 7. Oh, sorry. So Cresol Red would be yellow down here, yellow, 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 yellow. Just as we got to pH 7, it would start to turn red. And by pH 8.8, we'd be at red. So 8.8 is like here. Cresol Red would be yellow all the way up to our equivalence point, and then it would start to go orange right here. So if you were using this, you'd have to be watching for the tiniest little hint of orange, and that would tell you that you'd hit the equivalence point. And if you actually went until it turned red, that would mean you were a little bit too late. You'd have a milliliter or two of extra base before you got to your color change. So that's a maybe. Is there anything better? 1.2, 2.8, nope. 8 to 9.6, nope. Something that's around 7 would be nice. Hey, bromothymol blue would be a pretty nice choice because it'll start turning yellow, or it'll be yellow up to pH 6, and then it'll start changing maybe a little bit early. That might be easier to distinguish. It's hard to tell if you'd have to try this and see if it's easy to detect orange when it starts to appear in this indicator. You could use that. You could use bromo blue. Phenol red also straddles pH 7, which is nice. You could use that one, and again, it would be it's yellow, it's yellow, it's yellow. When it starts to go orange, that means the transition's begun, and you're probably around pH 7, and all these other ones are too high. So Cresol Red, Bromo Blue, or Phenol Red would all be reasonable indicators for this titration. Okay, let's try another one of these. A student recorded data for the titration of a sample of an unidentified acid, which they didn't say it's strong this time, so I'll just call it HA. And it's reacting with hydroxide. This will release potassium, and I don't care because potassium isn't an acid or a base. So this will give us the conjugate base of whatever our acid is and some water. They haven't said for sure that this is a monoprotic acid, that this will be 1-to-1, but I'm going to assume it is. If they don't say anything about like second endpoint or to completion, then you don't have much choice but to assume it's a single. So what does our pH curve look like? When we've added nothing, we're at pH 1. Go a little darker. Nothing added, pH 1. 5 mils added, we're up to 1.8. 10 mils, 1.9. 15 mil, we're up to 2. Whole lot of not much happening so far. 20 mil, we're up to 2.3. 25 mil, now it's starting to break a little, 3.1. Remember, we're expecting to see kind of an S-bend, so we expect this to break upwards, rise sharply, and then flatten out again. 30 mil, we're up to 5.3. 35 mil, we're up to 6. 40 mil, 6.3. 45, 6.8. 50, 8.0. 55, 9.9. 60, 10.5. And 65, we're up to 10.8. This is 11, so 10.8's like there. Well, not really the shape we were expecting, was it? In our first example, we got a nice thing like this. This one, if we connect the dots, let's see. Make that a little heavier. Instead of one big jump, this curve seems to have a couple. Seems to be a jump here, and a second jump up here. That can happen if you have an acid with two hydrogens on it, which means my assumption about HA was incorrect. This would make sense if, I'm just going to put an acid in here rather than calling this something mysterious. If you had an acid like, let's say, H2S, you could be starting down here with H2S. When you add base, one by one these turn into HS minus because they've given up one hydrogen. Then if you keep adding base, they give up a second hydrogen and become sulfide ions. So two jumps means two reactions, and for something like phosphoric acid with three hydrogens, you could even have jump, 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 curve like that, where there are three separate equivalence points. So that's more like the truth. This isn't just an HA, it's like an H2A. I'll call it H2A up here. I don't know precisely what acid it is, but it does appear to have two hydrogens on it. And so we have an equivalence point around pH 4, and then we have another one around pH 9. And we call this the first equivalence point and the second equivalence point. Okay. What's the concentration of the acid? Well, there's a couple of ways we could figure that out, because there are a couple of reactions that occurred. I'll show you both ways. First way, we could just look at this equivalence point and say, down here, we have added 1 mole of base for every mole of acid there was. So because this is the first equivalence point, down here we could say that the ratio of these things is 1 to 1. For every acid, there has been 1 base added. Or we could go up here, where the acid's been completely cleaned out, at the second equivalence point. And here we could say for every acid that we have, we've now added 2 base. One that stripped off the first hydrogen and one that stripped off the second. Both ways work. So if we run the math on, I'll do the first equivalence point because the numbers are a little simpler. We have our mystery acid reacting with a single hydroxide. That'll turn it into HA minus, and we'll get some water. The point is it's 1 to 1. And what information have they given us? They said it was 25 milliliters of acid. 0.025 liters. The KOH is 0.1 moles per liter. Moles per liter. And the other thing we know is, if we're right here on our equivalence point, then the volume of base that we've added is, if this is 25 and this is 30, is that 27.5? Is that fair? You don't get terrific values when you read these off a table because human eyes can only do so much, but that's what I get for the volume. Hopefully it's enough. We can get a number of moles off of that. It's concentration times volume, so 0.1 times 0.0275 is 0.00275 moles. These things are 1 to 1, so the number of moles of our acid must also be 0.00275. And from that we can get our concentration, which I'll put over here. Sorry for the weird layout. Number of moles divided by volume. So 0.00275 divided by 0.025. 0.025 equals, and I get 0.11 moles per liter. Significant digits, 3, 3. The trouble with this is that this looks like a 3 significant digit number, this volume that I came up with, but really, am I sure about that to the nearest tenth of a milliliter? Not so much. I think I'm fairly confident this is 27 point something milliliters, but calling it 3 here is super sketchy. I think based on the fact that I've read this, this is probably only good to the nearest milliliter or to the second significant digit, so I'm actually going to stand with 0.11 moles per liter. That's a judgment call, and we shouldn't pick on that when we're testing you, but just be aware, if you're doing a problem where one of the numbers came from you reading a graph, technically you should be trying to assess how precisely can I read this graph. And on a graph like this that doesn't even have individual milliliters marked, it's a little rich saying that you've got a number that's down to the nearest tenth of a milliliter. That isn't something you could honestly claim. So a number like that, probably pretty good. So concentration of the unidentified acid, check. What indicators could we use for this? Well, we'll go shopping for indicators, but we need some pHs first, so we know what to look for. It looks to me like this first equivalence point is right around pH 4, and the second one is right around pH 9, so nice round numbers. So 4 and 9. This is from a previous example. For pH 4, we're looking for something that straddles 4, so no, no, no. Methyl orange might do for the first equivalence point. Bromocresol green could work for finding pH 4. Too high, too high, too high, too high. Okay, so none of those are any good for the first, but we have 2 candidates for the first equivalence point, and the second one is pH 9, where that's a little too low. Thymol blue. You could watch for thymol blue to change from yellow to blue. Or what else is around pH 9? Phenolphthalein. Hard to pronounce, but a common indicator. Goes from no color at all to pink as you go towards pH 9, so you could watch for that. And none of these other ones catch pH 9, so I guess thymol blue or phenolphthalein for the second, methyl orange or bromo green for the first.